For question 1 of the review sheet, it says that we're taking line segment BC and we're rotating it 90 degrees. Remember that the capital R means rotation, and when it doesn't specify, we're always going to be rotating counterclockwise unless it specifically states that we're going to be rotating clockwise. So our rule for a 90 degrees counterclockwise rotation is our original coordinates are going to switch the order and the original y coordinate is going to change sign. So B, which is 5, 1, is going to become, so the original y is going to change sign, and they're going to switch the order. So that's going to be negative 1, 5 for B prime. And for point C, that's the point negative 3, negative 2. So the original y coordinate is going to change sign, so that negative 2 is going to become positive 2. And the order is going to switch. So that would be C prime. So here are our coordinates of B prime and C prime to answer the question. Okay, for number 2, let's take a look at which of the answer choices is going to carry the rhombus onto itself. So a 180 degrees rotation counterclockwise about the origin. So I don't know about that one. The origin is not exactly in the middle of this rhombus, so I don't know if it ends up looking exactly the same. I think we should put this one on hold and look at the other ones. Reflection over the line y equals 1/2 x plus 1. That has a y-intercept of 1. 1/2 x, that's a slope of 1/2. So that means we go up 1 and right 2, down 1 and left 2. Let's take a look over here. So we're looking for a line of symmetry. Remember, for these kinds of questions. So possibly, once again, let's put it on hold. We can come back to it afterwards. Oops, let me undo over here. There we go. The line y equals 0. So that's a horizontal line going through the y coordinate of 0 right over here. So that, in other words, that's the x-axis. That's clearly not a line of symmetry. And the line x equals 0, that's a vertical line. That's the y-axis. Oops. Hard for me to make lines on the computer today. There we go. And that is a line of symmetry. So that's the one we're looking for. Number 2, it could have been a line of symmetry, but not really. Number 4 is clearly a line of symmetry. So remember, with these kinds of questions, you're looking for either a point that's in the middle of the shape, like in the center, for rotational symmetry, or you're looking for a line of symmetry if it's talking about reflecting it over that line. Okay, we are reflecting in the line y equals x. That is the only reflection that I do recommend that you use the rule for. That rule is pretty simple. All you do is switch the order of the coordinates. So the new points that will be in the image of this function would be the point 3, 2, 7, 4, and 5, negative 1. So 5, negative 1 is the only answer choice that is here. So that one would be a point in the reflection. So for the line y equals x, just use the rule. You just switch the order of the coordinates. Okay, for number 4, we are translating. That means sliding it. And it says A prime is located at 4, 4. So A was 1, 3. And A prime is 4, 4. So the x coordinates are increasing by 3, and the y coordinates are increasing by 1. So the transformation is a transformation 3, 1, 3 to the right on the x-axis, and 1 up on the y-axis. So if I want to get C prime, point C is 4, 0, I can just apply the same translation. We can add 3 and we can add 1. So that would be 7, 1 for the point C prime. Okay, so we're rotating this pentagon around its center. So we have rotational symmetry. So let's do 360. That's a full rotation over the number of sides. 360 divided by 5 is 72 degrees. That's not a choice here, so we're looking for a multiple of 72. Let me try 108 divided by 72. No, not the whole number. 216 divided by 72. Yes, that one worked. So the answer here is 216. That is a multiple of 72. Okay, over here we have a dilation centered at the origin. So our rules apply. It's nice when we have a dilation centered at the origin, and the scale factors too. The equation of the line is this, and we need the line of the dilation, the image of this line after the dilation. So if I put this into y equals mx plus b form, let me do that on the side. Let me rewrite it here. Let me subtract 3x to the other side to move it away. So I have negative y is equal to negative 3x plus 4. There's an invisible 1 in front of the y, so I'm going to divide everything by negative 1 so I can get y by itself. So I have y is equal to 3x minus 4. So dilations preserve parallelism, so the pre-image and the image will be parallel to each other. And remember, parallel lines have same slopes. So our image, line M, I should say, line M, our image will have the same slope as the original line because they should be parallel before and after the dilation. Since it's centered at the origin, we can just take the y-intercept and multiply it by the scale factor. Negative 4 times 2 would be negative 8, so the equation of our line would be y equals 3x minus 8. Okay, moving along. Did I miss a question over here? Let me see. Let me scroll all the way down. No, I guess I just labeled these really incorrectly. Yeah, this is not number 9 and 10. Let me pause this a second so I can just make sure I didn't miss any questions. Nope, I just misnumbered this. Okay, so for number 9, which is not really number 9, let me graph this out. So let me make my coordinate grid over here. Okay, so I have 2, 6. That's point A. 1, 2. 1, 2, 3, 4, 5, 6. And B is 4, 2. There we go. Okay, so it says, is the image A prime B prime the same if it is reflected in the x-axis, then dilated by 1/2, as the image if it is dilated by 1/2, then reflected in the x-axis? So basically, does the order of those two transformations matter? So let's do it the first way first. Let's reflect in the x-axis. So the x-axis is here. So I'm just going to count the spaces to the x-axis. So wait, this was 2, 1, 2, 3, 4, 5, 6. That moved. I need to redo this. That's what I hate about doing this on the computer. My graphing moved. So 1, 2, 1, 2, 3, 4, 5, 6. Here is point A. And B is 1, 2, 3, 4, 1, 2. Okay. So to the x-axis, that would be 1, 2, 3, 4, 5, 6 spaces. So 1, 2, 3, 4, 5, 6 spaces to the other side would be right here. 1, 2, 1, 2 spaces to the other side would be right here. Okay. And then a dilation by 1/2. Remember, if it doesn't tell us the center of dilation, it's assumed to be at the origin. So we can take each of these points and we can multiply them by 2. So this is the coordinate 1, 2, -1, -2, -3, -4, -5, -6. So 2, -6 would become 4, -12. So I'm going to write that over here. A double prime would be 4, -12 after the dilation. And B prime is 1, 2, 3, 4, -2. So 4, -2, if we're doubling it, would become 8. Oh no, this is 1/2. This is not doubling it. My bad. Let's try that again. So you got to read the questions carefully here. I was looking at it as 2, but it says 1/2. So this is 1, 2, 1, 2, 3, 4, 5, 6. So 2, -6 would become half of 2 is 1, half of -6 is -3. So that would be 1, 1, 2, 3. That would be right over here. That would be 1, -3. And B double prime, 1, 2, 3, 4, -2. Half of 4 is 2. Half of -2 is -1. 1, 2, -1. And notice how it did get a lot smaller. It got half the size of the original. So here are our coordinates from doing it this way. Let's do it the other way with first dilating the points and then reflecting over the x-axis. So I'm just going to reset over here so that we can do it the other way. Okay. So if I take the original points and I multiply them by 1/2 to do the dilation first, A prime would be 1, 3. And B prime would be 2, 1. So let me write that down. Oh, wait, actually, I don't need to because I'm going to do the reflection next. So the reflection is the x-axis. So let's count the spaces. 1, 2, 3. 1, 2, 3. So that would be A double prime. And that is the point 1, -3. 1, 1 to the other side. That would be B double prime. And that is the point 2, -1. So they did end up being the same. They did end up having the same points. So it's not going to always work. The order does matter when you're doing a sequence of transformations, but here with this specific sequence of transformations, the order didn't matter. It was the same thing to do the reflection, then the dilation, as it was to do the dilation and then the reflection. It was the same thing. Okay, let's take a look at the next one. So if AB is congruent to DE, AC is congruent to DF, and angle A is congruent to angle D, write a sequence of transformations that maps triangle ABC onto triangle DEF. So with them telling us what's congruent between the two triangles, they're telling us what needs to match up at the end after the transformations. They're telling us what the corresponding parts are of the two triangles. And it doesn't look like the size changed. So we're not going to be doing a dilation here. They do look, and that makes sense because a dilation doesn't make congruent figures, but they did tell us that the corresponding sides here would be congruent, and so would the corresponding angles. So if corresponding sides are congruent, that means that they're congruent triangles. So we know that dilations don't make congruent triangles. They're not rigid motions. So we're going to be using rigid motions here. And to me, there could be other stuff involved, but it looks like it turned. So I'm thinking that we're going to need a rotation. So we can't just write a rotation and something else. It says a sequence of transformation, so it's going to be more than one. So we can't just say a rotation and then a translation. We can't just write that. We have to be as specific as we possibly can be. So let me just picture if I took this and I turned it just right where it is right now. A would be in the same spot as D. B would be in the same spot as E, and C would be in the same spot as F. So based on the triangle name, rotating it would make the orientation be the same as the way that it's supposed to end up. So in order to describe this rotation, I know that we don't really have a grid here or any numbers. So it's going to be hard to describe exactly how we're rotating it, exactly what the degree measurement is that we're rotating it. So before we describe our rotation, it might be helpful to first describe how to get this triangle in the same spot as this triangle, and then we can just turn it once it's already in the same spot. To get this in the same spot as this, we want C to come up here to where F is. So we're going to translate, and we're going to translate to the right and up along CF so that C matches up with F. So I'm going to write that down. Translation along CF so that point C matches up to point F. Because what happens then, if we bring this over here, and I'm going to try to draw this as best as I can, point C would be over here. Let me draw the rest of it. That would be B. And A. So what we could do now, if we do the translation so that it moves up to where point C is now we can just rotate it so that angle A matches up to angle D and AB matches up to DE and AC matches up to DC, because we know that angle A is supposed to be congruent to angle D, so they're supposed to match up. We know that AB is supposed to match up with DE, so because they're congruent, and we know that AC is supposed to match up with DC because they're congruent. So our center of rotation, since we already aligned this triangle with point C, would be point C, because then it wouldn't change. It would just stay in the spot and just turn, which is kind of what we wanted to do since we already translated it from here to here. So we want it, or point F, I should say, because we moved point C up to where point F is. So our center of rotation would be point F or point C. It doesn't matter which one you say. They're both in the same spot now, because then it would just stay here and it would just rotate to overlap with the rest. I'm just going to finish writing that response. So give me 1 second to finish writing that down. So I finished writing my response. So after the translation, that will move point C to point F. Our rotation centered at point F so that this point doesn't move, so that this just turns clockwise. That's the clockwise direction. So that angle A matches up to angle D, AC matches up to DF, and AB matches up to DE. So you can read my response here. Basically, the biggest takeaway is even when there's no numbers, even when there's not a grid, even if we can't specify the exact number of degrees that we can be rotating it or the exact number of units that we can be translating it, we do need to be as specific as we possibly can be. And if they give us information in the question about what's supposed to match up with what, we should also include that into our response to make our response as complete as possible. That was a hard one though. We're going to do the next one over here. This one is constructing the line of reflection between these two triangles. Let me get my compass. There we go. Let me move it down. Okay, So what I'm going to do to construct the line of reflection is I'm just going to connect point B to point B prime and C to C prime. A and A prime are far from each other, and you only need to connect two of them. So, oops. Oh no, let me try not to move this whole thing. Since a line of reflection is equal distance from the pre-image and the image points, because reflection is mirror image is equal distance, we're going to do a perpendicular bisector to make sure that our line of reflection is exactly in between the pre-image and the image points. And then let me come over here. Let me scroll up so I can see what I'm doing. Okay, and I'm not changing the measurement. I'm going to do exactly the same arc. Okay, right through those intersection points, here's my perpendicular bisector. So that's my line of reflection. To be 100% accurate, I should also do this construction again from C to C prime. I'm going to use a different color for that. And it should end up being the same line because it should be the same line of reflection since it's the same two shapes that we're reflecting. Okay, so more than 3/4 down, about 3/4 down, I should say. Same arc on both endpoints. And as you can see, it is the same. If we connect through, it's the same. So we found our line of reflection. Let me just put arrows on the end because it is a line. Okay, so here's our line of reflection, this line right over here, whatever it is. Mirror images on both sides of the line. Moving forward to number 12. Use the properties of rigid motions to explain why triangle ABC is congruent to triangle XYZ. So what happens here? So A matches up to X. So is that a rotation or was that a reflection? What happened here? So the way that I thought of it, and there's multiple ways to think of it, I'm sure you could do it with a rotation as well, but I thought of it as two reflections to get from one to another, a reflection over the y-axis and then a reflection over the x-axis, and that would match point A up with point X, point C up with point Z, and point B up with point Y, like it tells us in the naming that it should be. So a reflection is a rigid motion, and rigid motions preserve side length and angle measurements so they create congruent figures. Let me write that down over here. A reflection is a rigid motion. Rigid motions create congruent figures because they preserve side lengths and angle measurements. Moving along. So we have square, RSTV. This is a terrible looking square. And not the only way to label it, but if I did here R and here S, that's got to be T and V. Where RS is 9. And then we're dilating the square by a scale factor of 3. So not drawn to scale because obviously they look the same size. But if I'm dilating it by a scale factor of 3, if this one's 9, this one's going to be 27. What is the perimeter in centimeters after the dilation? Well, squares have all equal sides. So the perimeter would be 27 times 4, which would be 108. You could also get the perimeter of the original and then just multiply it by 3. So the perimeter would be 108. That's 27 times 4 sides. The area would be length times width. So that would be 27 times 27, which would be 729. 729 units squared. Okay, next one. So 1, 2, 3, -2, that's point A. 8, 2, that's point B. And 1, 2, 3, 4, 5, 10, that's point C. So the first part of the question is to graph and label this triangle, which is now done, almost. Now it's done. The second part is to graph and state the coordinates after a rotation of 180 degrees. Rotation of 180 degrees has a nice rule. All you have to do for that rule is change the signs. You don't need to switch the order of the coordinates. You can just change the signs of both of the coordinates. So A prime is going to be -3, +2. 1, 2, 3, 1, 2. So, right, just changing the signs, not changing the order. So that's -3, +2. So that's A prime. B is going to be -8, -2, -8, -2. And C prime is going to be -5, 1, 2, 3, 4, 5, -10. So that would be a rotation of 180 degrees. And remember, 180 degrees is the same in both directions. It's the same whether it's clockwise or counterclockwise. It will take your point and put it in exactly the same spot. Okay, then we are taking our image points. And what did I label that -10? That should be C prime. Because I guess I was thinking that was a y coordinate, -10. So now we are translating it and then dilating it. Remember when you see this symbol for a sequence of transformations, we're going from right to left. So we're going to translate and then we're going to dilate. So I'm going to take each point and I'm going to move 5 to the left and 2 down. And then I'm going to dilate by 2. So A prime is right over here. And let me move it 5 to the left. 1, 2, 3, 4, 5, and 2 down. So that's right here. So that's the point 1, -1, -2, 3, 4, 5, 6, 7, -8, 0. So that would be -16, 0. There's not enough space for that here. So I'm just going to write that over here. A double prime is going to be -16, 0. It's not enough space to go -16 units. So we can't graph that. Okay. B prime. We're going to go left 5 units. I can't even graph that. So let me write down this point over here. This is the point, -1, 2, 3, 4, 5, 6, 7, 8, -2. So if I take the point 8, -2, so I'm subtracting 5 from the x coordinate. So if I subtract 5 from the x coordinate, that would be 3. And I'm subtracting 2 from the y coordinate. So let me get my calculator. -2 minus 2 is -4. So that would be 3, -4. And then scale factor of 2 for the dilation. So that would be 6, -8 for B prime. So let me just alter that. That would be 6, -8. We can't graph this. It's asking for two big things. Well, we could have graphed this one. But to go left, it took us off the grid at first. Okay. And then C prime. So I can't go 2 down. I can't go any further down. So I'm just going to write down the coordinates again. So that's 1, 2. Oh no, that was -8, -2. Oh, I messed this one up when I subtracted. Redo. I'm always messing these up. -8 minus 5. Let's try that again. Is -13. And as we said before, -2 minus 2 is -4. So then when we dilate it by a scale factor of 2, that would be -26, -8. Definitely can't graph that on this grid. Okay, C prime is -1, 2, 3, 4, 5, -10. So if I'm starting with -5, -10, and I'm subtracting 5 from the x coordinate, that's what the translation says. So -5 minus 5 is -10. So let me write that here. That's -10. And -10 minus 2 is -12. And then it's a scale factor of 2. So that would be -20, -24. So let me write that down for C prime. negative 20, negative 24. Okay. There we go. So part D says, what is the ratio of the area of triangle ABC to triangle A prime, B prime, C prime? So the ratio of the area would be 2, or 2 to 1. You can write because, oh, actually, I should probably write that as 1 to 2 because it's the original to the dilated one. So the ratio would be 1 to 2 because the dilated one is double the size of the original one. So I didn't even have to do anything to think about that one. Rotations and translations are rigid motion, so they make congruent figures. So the area would be the same. That doesn't alter area because it doesn't alter side measurements. The dilation is the only one that alters side measurements, but it keeps everything proportional by a scale factor of 2. So whatever the area of the original triangle was, since we dilated by a scale factor of 2, the new one would be double the size, so it would be twice as large. So that would be a ratio of 1 to 2. Okay, moving on to the next one. Okay, we have 2 triangles here, and let A prime, B prime, C prime be the image of triangle ABC after a rotation about point A. Determine and state the location of B prime if the location of point C prime is -8, -3. So, oh, sorry, it's 8, -3. I can't read today. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Okay, so just from looking at how point C changed to point C prime, I see that it moved in a counterclockwise direction, and it doesn't appear to have moved too far. So I'm thinking maybe 90 degrees counterclockwise. Also, if you take a look, it's along the same perpendicular line here. So I'm thinking 90 degrees counterclockwise is what happened, but I want to test that out to be sure. So our rotation is centered at point A, and we learned about in class what we can do for rotations not centered at the origin. We can take our point, we can subtract off the center of rotation, so we can recenter it at the origin. We can do the rotation, and then we can put the real center back in at the end. It's 3 steps. So I'm just going to do that with point C just to see if it does bring us here, if it is a 90 degrees counterclockwise rotation. So the point C is the point 2, -9. So let me write down point C. That's the point 2, -9. And what I'm going to do first is I'm just going to subtract off the center of rotation, which is point A. That is 2, -3. So I'm going to subtract off 2, and I'm going to subtract off -3. So that gives me 0. That's really a plus. So that's -6. So now I've recentered this at the origin. And let me use my rule for 90 degrees counterclockwise to see if it's going to work. So that's, I switch the order and I make the original y coordinate the opposite sign. So when I switch the order, that's going to be +6. So that's after my rotation of 90 degrees counterclockwise. But it wasn't really centered at the origin, so I have to add the center of rotation back in at the end. So I'm just going to add back the center of rotation to -3, and that does give me 8, -3. So that is what happened here to bring point C to C prime. That was a rotation of 90 degrees counterclockwise. So now I figured out what's going on here. So now that I know it's 90 degrees counterclockwise, now that my guess was correct, I can do the same thing for point B to find point B prime, which is what the question's asking us, the location of B prime. So this is the point, -1, 2, 3, 4, 5, 6, -8. So 6, -8. Same thing, we're going to subtract off the center of rotation, which was 2, -3. So that gives me 4. It's really a plus, so that's -5. Now let's do our 90 degrees counterclockwise rotation. Switch the order. The original y coordinate becomes the opposite sign, so that would be 5, 4 when we rotate it 90 degrees counterclockwise. And then it wasn't really centered at the origin, so we do have to add our real center of rotation back in. So that would be 7, 1. So let me put that here. 1, 2, 3, 4, 5, 6, 7, 1. So that would be V prime. And A wouldn't change because it's our center of rotation. Everything's rotating around that point. It's not going to change. So if I wanted to connect it together to just see the whole figure rotated 90 degrees counterclockwise around point A. So the answer to the first part of the question is the 0.71. That is the new location of B prime after this rotation. And it's asking, is triangle DEF congruent to triangle A prime, B prime, C prime? Yes. To get from here to here, let's see what happens. So A is matching up to D. E is matching up to B prime. And F is matching up to C prime. It looks like a reflection happened from here to here. And reflections are rigid motions. They keep the sides the same length and the angle measurements the same. So they are reflections are rigid motion, so they will be congruent at the end. So that's the answer to part 2. Okay, over here, this is getting to be a pretty long video. How long is this already? Wow. Okay, so we're going to dilate by a center of dilation of 1/2. So I'm just going to connect point B to the center of dilation. And since we're doing a dilation of 1/2, we're going to perpendicular bisect. So I'm going to open up to about 3/4 of the way, arc above, arc below, over to the other endpoint. And I'm going to be as accurate as possible. I'm not going to be as super accurate, but we try to be as precise as we possibly can be. And right through there is our perpendicular bisector. So our point B prime would be that halfway point right over here. That's our point B prime. I'm going to do the same exact thing for the other pre-image points. So I'm going to connect point A. Oops, let me try that again. That wasn't super accurate. I'm going to connect point A. Why does it not want to connect well? Okay, that's as close as it's letting me do. For some reason on the computer, it doesn't want me to do it like slanted. I'm trying to get as close to it as possible. Okay, I think that's as good as it's going to get here. So what I'm going to do is I'm going to take my compass and I'm just going to do the perpendicular bisector again. Let me get some more space for myself. This time from O to A. Okay, so more than halfway down, doesn't matter exactly how much. Arc above, arc below, over to the other endpoint. There we go. And right through those intersection points. Oh no. This computer is freezing a lot. There we go. Let me try that one more time to connect the points. Yeah, it's just doing whatever it wants to do. It's not letting me go right through. But that halfway point, I was trying to go from here right through. This computer is being annoying today. But right over here, that halfway point, I'm as close as I can possibly get on this computer, which is being annoying. That is the point A prime. And I got one more left to go, so let me get a different color for my line. So I'm going to connect point C. Let me get the line again. To the center of dilation. There we go. That let me do it. And I'm going to take my compass and I'm going to do the same thing, the perpendicular bisector. And this is where it starts to get messy because I have a million different construction marks here. Okay, it's kind of messy. So I'm just going to take a totally different color, I don't know, orange, and I'm going to connect all of my image points. So the dilated triangle is in orange, and notice how it is half the size of the original. Okay, it does get messy. That's why I like to use different colors. If you're using a flat compass, you can stick different colors in. You can also use different colored pens to connect the lines together as well. Pen, pencil, black pen, red pen, blue pen. I recommend different colors bringing with you. Okay, over here we're dilating by a scale factor of 2. So we are moving each of the pre-image points double the distance from the center of dilation that they are right now. So using my straight edge, I'm just going to connect from the center of dilation through the pre-image point. I'm trying to get through point A as best as I can. Sorry, this is taking a long time. Okay, it's as best as it's going to get. And I did send a bit because that's going to help me find my image point afterwards. So what I'm going to do is I'm just going to measure from the center of dilation to point A. So, oops, I didn't want to do that. I want to just measure as best as I can. Now I got to open up a little bit more. On the computer, it is so hard to measure things accurately. Okay, there we go. I'm going to put an arc to show I measured. So that's the distance from the center to point A. So I'm going to come over here and I'm going to double that distance. There we go. And that is my point A prime. It is double the distance away. I don't think I can fit these on my computer, these other ones. It's the same idea for the other ones, but I don't think I have enough space here. So, oh, maybe I do. We'll see. I'll just go into the next question. Okay. Let's do the same thing. Let me get a different color. Let me measure. Put an arc to show I measured. And double that distance. One more to go. Let's see if I can fit it here. Hopefully there's enough space. Yeah, there is. Perfect. Oops. Let me get a different color. Same thing again. Going to measure. I hope my compass can open that up that wide. It cannot. That's the other annoying part about doing this on the computer. So it's about, I would say about here. That's the annoying thing about doing this on the computer. I couldn't accurately measure from here to here. My compass does not get any bigger on the computer. Okay, and if we connect together our dilated triangle, oh no, how did it not do a straight line? our dilated triangle should be double the size as our original one, or as close to double the size as we can get it. Okay, moving down over here, these are the challenge questions. There's multiple answers that you could do. So I would say here, a rotation would probably be the easiest, but it does say a sequence of transformations, so you do have to put more than one if it says a sequence of transformations. It could be 2 rotations following each other. So let me try a rotation here and see if that accomplishes it, like I was thinking. So to move from here to here, I'm thinking 180 degrees. So the rule for that is that you change the signs on your coordinates. You don't have to change the order, but you just change the signs. So point A is -1, -2, -3, 1, 2. So -3, 2 would be 3, 1, 2, 3. -3, 2 would be 3, -2. So that would be 1, 2, 3, 1, 2. That would be right here. So notice it doesn't put it exactly where it needs to be. Let's keep going. 1, 2, 3, 2. So that would be -3. 1, 2, 3, -2. Once again, doesn't put it exactly where it needs to be. C, that's 1, 2. 1, 2, 3, 4, 5. So that's 2, 5. That would be -2. 1, 2, -5. 1, 2, 3, 4, 5. Not exactly where it needs to be. And point D, -1, -2. 1, 2, 3, 4, 5. So that would be 2. 1, 2, 3, 4, 5. So all the points are oriented the way that they need to be. So we're good on that. It's facing the correct way after the rotation, but it doesn't exactly match up. So it looks like we're going to also have to slide it a bit. So it looks like if we slide down 2 units here, that would be good. And down 2 units here, down 2 units, down 2 units. So that's a translation of down 2 units. So a rotation of 180 degrees, doesn't matter which direction, centered at the origin. That's how we were able to use the rule. We centered at the origin. Then a translation 2 units down. And that would work. So that's a sequence of transformations. It is 2, more than 1. Okay, let's take a look at the next one, the last question here. We have to do a translation 5 units to the right and 2 units up. That's easy. 1, 2, 3, 4, 5, 1, 2. 1, 2, 3, 4, 5, 1, 2. 1, 2, 3, 4, 5, 1, 2. Followed by a reflection over the line y equals 0. Y equals a number is a horizontal line. The y coordinate of 0 here is here, so that's really the x-axis that we're reflecting over. Not bad at all. 1, 2, 3. 1, 2, 3. Mirror images, equal distances. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And the question says graph and label. Oh, A prime, B prime, C prime. There we go. It doesn't say we have to actually write down or state the coordinates. So we're all done. That was a long video.